All right, in this lecture, we're going to talk about supercritical fluids and vapor pressure. And we'll start out here talking about supercritical fluids. Previous lectures, we talked about heating diagrams, we talked about viscosity and surface tension and capillary action and intermolecular forces. And now we're building towards the phase diagram. But there's a couple things we need to understand first before we get to the phase diagram, and that's supercritical fluids and vapor pressure. So let's start out with supercritical fluids. Now, if we think about a gas that is trapped in some container, we know a gas is sort of characterized by low density, right? So there's molecules and they're pretty spread out here. Now, if I push on this, so now let's imagine the top of this container is actually a movable piston that moves up and down, right? And I can push this part of the piston down. Okay, so if I do that, now my piston, maybe it looks something like this. I've moved the piston down quite a bit. And of course, doing so brings these molecules closer together. And you can liquefy this, right? What you're doing is bringing these gas molecules close enough that their intermolecular forces take over, right? We learned from previous lectures that, the phase of any compound, any molecule, depends on a balance of the temperature, which really is its kinetic energy, versus the intermolecular forces. So here, if I bring the molecules close together, I let these intermolecular forces take hold, right? That's one way to liquefy this gas. Now, the opposite is true, of course, also. If I increase the temperature in this liquid, the molecules will have enough kinetic energy to overcome this intermolecular force and enter the gas phase. So you can go back and forth between gas and liquid by, heating things up, cooling things down, increasing the pressure, as I'm showing here, or decreasing the pressure. But one fascinating point is that there is a temperature, a kinetic energy, beyond which you cannot compress it from a gas to a liquid. So what we're showing here is going from a gas to a liquid phase, but there is some temperature, i.e. kinetic energy, where these molecules simply have too much energy and they're, roaming around too fast, they have too much energy, the intermolecular forces never take hold, okay? That temperature, beyond which we can't compress it to a liquid, is known as the critical temperature, right? The pressure needed to compress it. So if we're at exactly that critical temperature, the pressure needed here, right, put on by this piston, this piston pressure, that pressure needed at this critical temperature is called the critical pressure. And if we go to any temperature higher than this, right, any temperature above this critical temperature, we enter, and this is a supercritical point, so pay attention, we enter what's called a supercritical fluid, the state beyond this critical temperature. Okay, so again, these states of matter are always a balance between the intermolecular forces and the kinetic energy, but there does exist this temperature called the critical temperature, beyond which it doesn't matter, right? And what we do with the pressure, we can't get it to go from a gas to a liquid phase. And that is when it's a supercritical fluid. It will have properties unlike a solid, liquid, or gas, and it is sort of the fourth state of matter. Okay, and you need to appreciate that this is not just some, distribution of liquid molecules and gas molecules, but it is really a new state of matter where the molecules have properties of both liquid and gas. It is not that there is a pocket of liquid and a pocket of gas. No, it is a completely uniform new phase of matter known as a supercritical fluid. And so we're going to watch a quick video here on what that looks like. And what we're looking at here is sulfur hexafluoride, SF6, in a stainless steel container. And what we're going to do is heat this up, okay? And as we heat it up, we see this liquid. What we're looking at here is very much like what you would see if you had a glass of water, right? Liquid water at the bottom, gas on the top, and this meniscus in between. But here we have sulfur hexafluoride. There's liquid sulfur hexafluoride at the bottom. There's gas sulfur hexafluoride at the top. Now, what we're going to do in this closed cell is we're going to heat this SF6. And, well, when you heat a liquid, we expect it to boil. But as it boils, the pressure in this device, because we're evolving more gas molecules, the pressure will go up. Okay? And we'll keep heating, the temperature go up, and the pressure will go up until we reach this critical temperature and critical pressure. And if we increase the temperature beyond that, we will enter the supercritical state. Okay? And so that's what we're going to see here. So at the start of the video, we're heating this, right? We're heating this, and we'll start to see a couple bubbles, right? There they are, as this sulfur hexafluoride is entering the gas phase, right? It's starting to boil. Well, that's good. But the pressure is also going up because now we have more gas molecules. And we're going to keep heating this and keep heating it and keep dumping energy in. And now something kind of interesting happens, right? You would usually expect all the liquid to boil, right, and turn into the gas. But what we're seeing is the meniscus here in the middle is moving and thinning out, okay? So when we move beyond this critical point, when the meniscus completely disappears, right? And I want you to appreciate that it's not that we are converting all the liquid to a gas. No, what's happening here, and you can tell we're not. Why? Because there's still, look at all this liquid down here. Even here, there's still all this liquid. But this meniscus is about to disappear. And when it disappears, it means the sulfur hexafluoride throughout will now be a supercritical fluid. It will not be some pockets of gas and some pockets of liquid, but it'll be one uniform state of matter, the supercritical fluid. So we keep heating. There's still just the faintest line here that is the meniscus, and it's gone. Okay, so now we're in the supercritical state. No, it doesn't look any different. It's not crazy looking. It's not chaotic, but it is a new state of matter. You can take, density measurements. It's neither the liquid density or the gas density. And supercritical fluids are pretty neat because they have properties of both gases and liquids. And so back in the day, a lot of people used carbon dioxide actually as a supercritical fluid for dry cleaning. And so if you have supercritical carbon dioxide, well, it has, the dissolving properties of a liquid. So it can dissolve stains, right? And it has the penetrating and, diffusiveness of a gas. So it gets in all the nooks and crannies like a gas would. And so supercritical carbon dioxide was used as a dry cleaner at one time because it had both of these dissolving powers of a liquid, but also the penetrating power of a gas. So this is now supercritical SF6. And what we're about to show here is sort of the opposite process, is coming out of this supercritical state and separating into the liquid and gas phase. And this is my favorite part. We'll play it again from the beginning. We're boiling. We're going to enter the supercritical state here as the meniscus disappears. And then we're going to very quickly lower the temperature and pressure. And what we'll see is a sort of reverse boiling as the two phases of matter separate. Here it comes. 3, 2, 1. Now they're separating. And you get this sort of cool, chaotic, reverse boiling type of phenomenon. I'll play it again here. We're in the supercritical state, and now all of a sudden we're going to lower the temperature and pressure really quick. And once we do so, we will separate out the liquid and gas and reestablish the meniscus. Boom. Okay, so that's a supercritical fluid where we're moving beyond this critical temperature, beyond which it doesn't matter how much I push on the molecules, they don't set up a liquid state ever again. They're in this new state of matter. Okay, so that's supercritical fluids. One more thing we have to talk about before we get to phase diagrams in the next lecture, and that is vapor pressure. And this, maybe more than any other concept, illustrates, conceptually the difficulties in a class like General Chemistry 2. And so I want to take some time on vapor pressure, because if we can really master this, it really goes a long way to what I like to call thinking like a molecule, right? Conceptually imagining you are the molecule and how you behave. Because, if there's one thing I know, it's not super important for you to memorize every single thing you learn, right, in chemistry. It's much more important you master the basics, learn the fundamental behavior of molecules, and then you can piece it all together to sort of, logic your way to an answer a lot of times. And so I think vapor pressure is one of those concepts that's a really good exercise to try to master these conceptual fundamentals. So vapor pressure is a measure of, temperature is a measure of the average motion, but within, a mole of molecules, there's a real distribution of energies. And so before we get to actually thinking about vapor pressure, let's think about what temperature really is, right? And I've said often that temperature is an average kinetic energy. So even the air molecules around you right now, some are moving fast, some are moving slow, some are moving medium. Okay, just because the air around you is at 25 degrees Celsius doesn't mean all the molecules have the same energies or the same velocities. So if you think about, the air molecules in the room around you, some are moving really fast, some are sort of kind of slowly careening off the wall, and some are moving at some medium speed. So a lot of times, I'll say energy and average energy, but, it might be easier to think in terms of the velocities. Okay, so there's a distribution of speeds. Now, as we shift the temperature and bring the temperature in the room up, more of these molecules will be going faster. There's still a distribution, but, now on average, they have more energy, they have a faster speed, it's a higher temperature as I move from low temperature to high temperature. And that's what this graph is showing, right? These shapes of these graphs are known as a Maxwell-Boltzmann distribution. And on the y-axis, it's the number of molecules, and on the x-axis, it's the kinetic energy that they have. And so at low temperature here, maybe this is 300 Kelvin or something, versus some high temperature, maybe 500 Kelvin. These are the two shapes of the curves, okay? What it's showing is that, there's an awful lot of molecules, this many molecules, with this molecular speed or this kinetic energy, right? So yes, in the blue case, I suppose I could draw in blue. In the blue case, there's this many molecules moving slow. There's this many molecules moving medium. And there's this many molecules moving fast, if we wanted to call that slow, medium, and fast. And there's actually a little bit of molecules out here that are moving very, very fast. Now let's think about the red curve. Now your medium, right, your peak of the energy, there's this many molecules, but that middle of your distribution of speeds is pretty much equivalent to the fast portion of your low temperature molecules. So again, imagine a whole bunch of molecules in a container, some going slow, medium, fast. At this low temperature, most of them are going this speed. At 500 Kelvin, most of them are going this speed, which only a very small portion of the molecules had in your low temperature case. So as the temperature rises, the fraction of molecules that have a very, very fast speed or a very, very high energy increases. This is a whole lot more area under the curve than this was. And so this is important for vapor pressure and actually important for chemical reactions and activation energies and that sort of framework as well. These speeds, again, come into play. But here in vapor pressure, it's important because there is some, kinetic energy the molecules need to enter the gas phase. So in thinking about vapor pressure, what we're really thinking about is these liquid molecules. Maybe it's water. And maybe I'll actually draw them as spheres because it'll make the drawing easily. It'll make it easier for me to show you what I'm talking about. So these water molecules, some are moving slow. That's a small arrow. Some are moving medium. And some are moving fast. Okay, low energy, medium energy, high energy. But remember, there's gravity that is pulling down. There is hydrogen bonding from water molecules down here that is pulling it down. And so this molecular speed of this water molecule is not enough for it to leave the liquid phase entirely. So that one stays as liquid, that one stays as liquid, but this one has a really high energy. It's one of these molecules that there's a distribution of speeds. It is one of the molecules over here at 300 Kelvin. And it has enough kinetic energy to surpass this vertical line I'm drawing here and enter the gas phase. And so what happens is, as I go to this higher temperature, more of the water molecules are moving very, very fast. And so more have enough energy to leave the liquid phase and go to the gas phase. And so as the temperature rises, the fraction of molecules that have enough energy to break free of all of these hydrogen bonds that are holding them down, all of the gravity that is holding it down, more of the molecules will have enough energy to overcome all those forces and enter the gas phase. Okay, so all that relates to vapor pressure, because vapor pressure is the pressure of the gas phase above the liquid phase. Okay, so let's think about a closed container. And let's think about water molecules down here. Now, I pour some liquid in here, I close the top. I use a vacuum or something to evacuate all the air above this. So now it's just liquid molecules at the bottom, and I hit go, right, on my stopwatch. Okay, well, these exist at some temperature. Some are moving slow, some are moving medium, and this guy's moving fast. Okay, the slow and medium don't have enough energy to overcome the intermolecular forces holding them down, overcome gravity holding them down, but this one does, right? And it goes zooming off into space, careening about. So now it's up here. Now, sometime later, this molecule will careen off of here and re-enter the liquid phase. Just so we keep track of him, okay? So as I hit go on my stopwatch, some of these molecules will have enough energy to leave, and others won't. And so what plays out is the following movie, right? Some of these leave, maybe this one, and this one, right? And so now I have 3 molecules up here. Freeze frame. That's what it looks like. Well, now this water molecule that also had a lot of energy before, well, now it's at the surface. It moves up here, and now it also has enough energy, and it starts to leave. But fast forward in time, these have careened about. There's still 3 up here, and this one's entering the gas phase. So now I have 4 up here. 1, 2, 3, 4. Hit play again. Well, now this one's coming back down and gets deposited here. 1. This one approaches the surface but isn't there yet, 2. And this one's colliding off this wall, 3. And this one's bounced over to here, 4. But also at this time, this other molecule has moved over, approached the surface, and it has enough energy to leave. So now molecule 5 is leaving. Okay, what I'm trying to show here is that this is a very dynamic system. Okay, it's very chaotic. But the good news is the rate of these things leaving will eventually equal the rate of these things returning. So that, after I wait 30 seconds or so, I don't really care about keeping track of these. I know at any one point in time, there will be an average of 3 molecules up here. Right? And most of the molecules in the liquid phase. Okay? Those same 3 molecules will at some point re-enter the liquid phase, but by the time they do, 3 different ones will have escaped. Okay, and so it's very important to realize that at the microscopic level, this is a really chaotic system. Waters are constantly going up and getting kicked up into the gas phase. And they're, jostling around, chaotically bouncing off one another and the walls of the container, but they're re-entering the liquid phase. But when the rate of re-entry equals the rate of entering the gas phase, those two rates exactly offset, and you have a net effect of roughly 3 molecules of water in this case in the gas phase. Okay, so this liquid and vapor reach what's called a state of dynamic equilibrium. One of the most confused concepts in all of chemistry is that equilibrium means nothing is happening. Wrong. Equilibrium means a whole bunch of stuff is happening, but it's happening at equal and opposite rates. Okay, you can have a reaction that is going forward and backwards. It achieves equilibrium such that the forward reaction is the same rate as the reverse reaction, even though reactants are still turning to products and products are still turning into reactants. The same thing is happening here. Liquid is going to gas and gas is going to liquid. If you watched a movie at the microscopic scale here, it'd be really chaotic. But overall, those rates balance each other out and achieve a dynamic equilibrium. And now we establish the concept of vapor pressure. Vapor pressure is the pressure that these 3 molecules in this picture exert over the area of the container. That is the pressure, force over area. That is my vapor pressure. But it is only for this one component substance, just water, in this closed container. And that is the vapor pressure. Okay, so it's this dynamic equilibrium that is established, where equilibrium doesn't mean nothing is changing. It's just they're equal and opposite processes, and the amount of gas you then have in the vapor phase will exert a pressure, and that is the vapor pressure. So, why is vapor pressure important? Well, it turns out this pressure that it exerts governs when the liquid boils. Okay? The boiling point of a liquid is the temperature at which its vapor pressure equals the external pressure. So, what we did special here was we closed this container. Okay? We closed this container, but what if, imagine, in a world where this container is open, now there's something else we have to take into account. And the something else we have to take into account is that there's air molecules up here pushing down on the liquid surface. But at some temperature, these molecules will have enough energy to overcome this air pressure force and enter the vapor phase. That temperature at which this natural vapor pressure of that liquid is equal to the external pressure applied by the air, that's what we call the boiling point. Okay, so vapor pressure is really important to establish the concept of a boiling point. The normal boiling point is just sea level pressure. Okay, so normal boiling point is the temperature at which the vapor pressure is equal to atmospheric pressure at sea level. So let's look at some different chemical compounds and the temperature they boil at. What is their normal boiling point? So here is the line for 760 torr, or 760 millimeters mercury. That is the atmospheric pressure at sea level. 760 torr, or 760 millimeters mercury. Water is over here 100 degrees. It's 100 degrees Celsius because it's got a lot of hydrogen bonding, so it's staying in the liquid phase. You really have to heat it a whole bunch until you can overcome those hydrogen bonds, get enough molecules into the vapor phase to exert a vapor pressure that is high enough to overcome atmospheric pressure. Okay, so the vapor pressure of water is 760 torr at 100 degrees Celsius. So that's the boiling point. That's where water's vapor pressure equals the external pressure. For ethanol, right, it's got a hydrocarbon chain. It still has some hydrogen bonding, but the hydrocarbon chain sort of weakens the intermolecular forces as a whole. So it doesn't take as much temperature to get its vapor pressure to 760 millimeters mercury. So that happens at about 80 degrees Celsius. And diethyl ether, no hydrogen bonding, it's able to enter the boiling, it's able to enter the vapor phase, it's able to boil at 34.6 degrees Celsius. You only have to give it a little bit of energy for those molecules to overcome their intermolecular forces to create a vapor pressure that equals this atmospheric pressure, i.e. the boiling point. So we can also think about, not everybody lives at sea level, but these curves are then useful for thinking about, what if you lived, like I did, in Albuquerque? And so Albuquerque, I think, is somewhere like 630 torr, so maybe it's here. And so maybe that means the water boils at, I don't remember what it was, but maybe 95 degrees Celsius. Okay, so maybe I only have to get to 95 for enough water molecules to get into its gas phase to overcome the air pressure. Why? Because the air pressure, when you're a mile up in Albuquerque, the elevation is a mile, there's less air above you if you're already a mile up above sea level. So the air pressure is less. So the boiling point is less at altitude. Okay, so when I lived at Albuquerque, a mile high, there's less atmospheric pressure, so less temperature is needed to overcome that downward force from the atmosphere sitting on top of my boiling pot of water on the stove. Now, that sounds like good news. It's actually not, right? Because I'm a good Southern boy, I like my grits, and my grits I have to cook in boiling water. If the water is only boiling at 95 Celsius, my grits, your pasta, takes longer to cook because you're cooking it at a lower temperature. Remember our previous lectures on heating curves? When the thing is boiling, it's just statically sitting at 95 Celsius in Albuquerque, whereas in Florida at sea level, it's sitting at 100 degrees Celsius. And so your pasta or my grits cook much faster at sea level because the temperature of the water it's in is much higher. So, how do you get around this? Some cooking advice, where if you're living a mile high and the pressure is lower than it otherwise would be, buy a pressure cooker. Okay, that brings the pressure of the atmosphere, it encloses it and brings it up such that your pressure is somewhere up here and your food is able to cook at 105 degrees Celsius. Your food cooks in less time because the temperature it's cooking in is higher. Now, you can actually quantify this, right, with an equation that looks like this, the natural log of this pressure, right, where this is the vapor pressure here. We'll call it P vapor, of a liquid is inversely proportional to its temperature, and it has something to do with the delta H vaporization, right, the energy it takes to actually liberate the liquid to the gas phase. Now, if you know anything about calculus, this is actually a differential that you integrate, and well, you're able to set up, or actually this is the integrated form already of the differential, and you're able to set up final and initial conditions such that you can use this equation here. Both are technically called Clausius-Clapeyron, but this is the one I use a lot in class. It ends up being more useful for the types of problems, right, that we're going to do. One thing you need to note here is that for this equation that you really need to know and how to use, you really need your temperatures to be in Kelvin here. So don't use Celsius, don't use Fahrenheit. Pressures have to have the same units. It doesn't matter if it's torr or atmosphere, whatever you like, but as long as they're the same, okay, one unit divided by the other will be fine. Your R here is 8.314 joules per mole Kelvin, the gas constant. And if you're using that R in joules, just make sure your delta H here is also going to be in joules. So let's actually look at something like this in practice. Let's take this and apply it to a problem. You can apply it actually, to the Albuquerque example, right? For something fun, look up the delta H vaporization of water, look up the pressure in Denver or Albuquerque or someplace that's a mile high and calculate explicitly what the temperature is that water will boil at. But here we're going to do a slightly different problem. Let's look at this. Ethanol has a heat of vaporization of 40.5 kilojoules and a vapor pressure of 115 torr. at 34.9 degrees Celsius. At what temperature is the vapor pressure 760 torr? Report the temperature to 3 sig figs and units of degrees Celsius. Whew, so this looks overwhelming, right? For these long word problems, the best sort of advice I can give you is to read it through once like we just did, read it through again, and write down the bits of information that are most useful. So ethanol has a heat of vaporization, delta H vaporization, we're reading it through a second time here, of 40.5 kilojoules per mole. Okay, I know just from experience that I'm going to want this in joules per mole. So I'm just going to immediately convert this to joules per mole, because I know my gas constant is always going to be in joules per mole, at least the way I like to use it. Okay, so I keep on reading, and a vapor pressure, so that's P, and it's the first pressure I'm reading about, so I'm going to call it P1. A vapor pressure of 115 torr at 34.9 degrees Celsius. So that is the temperature, T1, that goes with my pressure, P1. And T1 here is 34.9 degrees Celsius. But I remembered that Prof just yelled at us that the temperatures must be in Kelvin in all caps with 3 exclamation points, so I know it's important. And so I'm going to convert this 34.9 degrees Celsius plus 273.15. And now I have 308.05 Kelvin. I keep reading. At what temperature T2 equals question mark is the vapor pressure P2 760 torr? Report the temperature to 3 sig figs and units degrees Celsius. Okay, so we've read it through a second time, we've written things down, and now it's plug and chug. I'm just putting these bits of information into this formula. So natural log of P1 over P2, 115 torr, over 760 torr. Again, you can convert them to whatever pressure unit you like as long as they're the same. That'll be just fine. This is equal to delta H, 40,500 joules per mole, over 8.314 joules per mole Kelvin. So joules per mole cancels out. This over Kelvin, 1 over Kelvin, means the unit is going to come up here and just be Kelvin in the end. And then I have this latter part here, 1 over T2, 1 over T2, which I don't know. That's the question mark, so I'll keep it there, minus 1 over 308.05 Kelvin. And now it's straightforward, the natural log. Maybe we'll move this over. Natural log of 115 over 760, I think comes out to like negative 1.8884 or so. This 40,500 divided by 8.314 looks like about 4,871. And then you have 1 over T2 and 1 over 308, which is like 0.00324. And I'm just solving for T2. We're dividing both sides by 4871. We're then adding this to the other side. All of that in the end gives you a number like 0.002858 equals 1 over T2. So T2 is 349.84 units Kelvin. Now, finish the problem. This looks good. I go back and read the problem one more time, and I see at the end reported in 3 sig figs and units Celsius. So don't forget at the very end to convert this back to Celsius, minus 273.15. For the final answer of 76.7 degrees Celsius. And that's it. So now that's about as hard of a question as you're going to get in general chemistry 2 for Clausius-Clapeyron, and vapor pressure. So if we can master that, we're good to go. So in this lecture, we covered vapor pressure and supercritical fluids. This now gives us all the information we need with previous lectures to discuss phase diagrams, which is what we'll get to in the next lecture. So that'll do it for this lecture. I'll see you next time for phase diagrams.